Um, Hi everyone. My name is Aditya Sinha, and this is my first video on YouTube. And I just wanted to give it a try, like if I am able to explain things or not. And this is specifically for knowledge purpose, and I'm not a great YouTuber or something like that. So, my interest lies in data stores and machine learning, data science, software development, data engineering, and definitely coding and programming. So I generally delve in those areas. I learn a lot, and I want to be better on that. So today I will be talking about one of the papers, that is scalable garbage collection for in-memory MVCC systems. So in this paper, this is the paper that I'm studying in University of Southern California, and this is my second semester, and I have taken this semester advanced data source, where I have to present this paper to the team. So I want to give it a try. So let's see how it goes. So the scalable garbage collection for in-memory MVCC systems is uh, it's an existing garbage collection method that like which struggles with STAP workloads, which is hybrid transaction and analytical processing. What does that mean is that we know that there is OLTP as well as OLAP, right? So this is for transactional purpose, and this is for analytical. So transaction probably means crowd operations, where you go into a table, there are multiple tables, tuples, and you do either create a tuple or read a tuple, update or delete. In the analytical, it's like there is multiple tuples and there are columns as well, and for each column you want something like if 1 2 3 4, so you might mean the average, which will be 7 9 10 by 4, which is 2.5 or something like that, which delves into the analytical part of the database. So that's probably what analytical means, and transactional probably this is more on the direct approach, where I don't have to do anything and it's just give and take. Analytical, you might need to do pre-computations, and that's where the things gets interesting. So I'll just remove this. Now HTAP means something like that, which is that you have to do something as hybrid transaction and analytical processing. And there's one other thing that you should know is MVCC, which is multi version concurrency control. So what does this mean is that, let's say that you have a big table where let's say there's a one guy who has wants to read tuple 1. Now there's another person who also wants to read it. Now we know that if two people are reading at the same tuple, there could not be any issues because there's no changing and both can read it together. The problem happens is that when this third guy, C, who wants to write or update or delete it. So what happens is that if C has come first, or let's say A has come first, and he has started reading it, and it takes around, let's say, 5 seconds, and it's starting from t0 second, or I should use some other term, which is let's say time 0 to time 5. Now in between C comes, and it starts at time 1 and ends at time 4. This is just hypothetical. And so what happens is that while reading A, C updates it, and A doesn't is not probably aware of that. And what happens is that this can create conflicts, and that's how the problem starts to arrive, and that's where MVCC control comes into the place. So now, why what is probably one of the methods that traditional people follow is that once someone is writing it, it locks it, like no one reads at that time. Or if someone is reading it, then they put a read lock, like someone is reading it, so once someone like is reading it, C cannot go into that and update it at that time. But there is lots of pros and cons in this situation, because let's say that uh, this A reading takes a lot of time, so C has to wait for that. And uh, like it can take 100 seconds, or let's say it's more than that, or this process is very slow. So what happens is that C waits forever, and it causes starvation. So this is not correct for something like a database, because database can be used for finance, banks, by some government, and they don't want inconsistent data or slow data, or inaccurate data, or something like that. So for this, MVCC came into place. Now what MVCC does is, if someone A is reading it and B is reading it, so both are fine. But if C starts to read it, then it has to create a new snapshot, or in layman terms you can call versions. So you can create a version 2, you go and write in this version 2 everything C writes here, while A and B works on the version 1. And then once this writing is done, and this whenever it's completed, it goes back and updates it after that. But so the importance or the pros of this method is that it doesn't create any starvation. So C can just directly update it and go back and say to the owner or the process that this has been completed. Same way A and B doesn't have any concurrency problem, not concurrency, like consistency problem, or any slowness in this regard. So everyone is happy at the end. So this is how this happens. So it's pretty much a big topic, which is MVCC, but I have given you the crux of it, like what's the basic uh, thing that it can do. Now coming back to scalable garbage collection for in-memory memory system, as the title of this suggests, that it creates a scalable garbage collection for in-memory. So what happens is that when you create a MVCC where there are multiple tuples, and for each tuple you create version 1, version 2, and so on. So you know that at the end there should be a latest version which everyone should follow. This is the latest one, and this becomes obsolete. So we would at one point of time want to remove it, prune it, or something like that. So for that, we need a scalable garbage collection, which doesn't create a memory have overhead, as well as it doesn't become inaccurate. It should not create computational overhead and something like that. So this paper is built on that. So this is the basic of this paper's um, motto. Okay. So now, just to give some basic information, that this has been written by four authors who work in uh, these universities, and let's look into some of the things that they have shown in this paper. So one of the things that it talks about is vicious cycle. So what it says is, if there is long running transactions, or like there are long range transactions, then it can create a limited garbage collection problem. As in, like, when there are long running transactions, you do not want to remove those transactions because it's still running. So you can only remove the obsolete versions, which can be limited because of the running transaction, and it has not even become obsolete. So if this is limited, then there could be a problem of more versions, like more number of versions can be created, and the garbage collection will not be able to destroy it or prune it. So what happens with number of versions, that it creates a performance overhead. And once there's a performance problem, so more versions create longer version chain, because as you can say that there is version 1, version 2, version 3. Now everyone is, some of them transaction is pointing at version 1, some version 2 and 3. So now, if a new process comes, they have to navigate to all of them to find like which version I have to take. So that creates more versions. I'll be I'll talking about the next steps in another video, because I have to go, and I'll